Welcome back to the Rad Lab podcast. I am Dr. David Dan, and with me is Dr. Dale Ensor. This podcast is presented to you by the chemistry department at Tennessee Tech University. This podcast deals with anything and everything radiochemistry, and for this main series we have going currently, it's going into the history of radiochemistry, covering everything from the start, like the first episode where we talked about X-rays. And now we're going to be going into Becquerel and following that story as we go.
We ended the last time with Röntgen and his discovery of X-rays. Interestingly enough, he established his scientific credit by mailing a copy of the paper, which was published around the world, basically, to well-known physicists and scientists around the world to establish his credibility. But he refused to do anything about patenting X-rays because he felt like it was a discovery that was the property of humanity, and he did not wish to profit from it. Even though within a month or two it was already being used medically, and his report, just showed how quickly something like this gets applied with especially the medical applications. And so once Röntgen announced the X-rays, then there became a immediate search for other material that would give off X-rays.
So the tubes weren't enough.
Right.
So they were looking for natural sources of X-rays.
That's right. There was an article published by a prominent French physicist who thought that maybe the luminescence was also accompanied by X-ray emissions. So people began to look for luminescent material that would also give off this penetrating X-ray. Now, Becquerel, Antoine Becquerel, was the son of a very famous French physicist who had been the director of the Paris Museum of Natural History. Becquerel's father had been interested in luminescent material, and so he had used his position in the museum to make a large collection of all the luminescent material. Now, luminescent material are materials that absorb light and then re-emit it. And if it's instant re-emission, it's called fluorescence. And if it goes on after the initial source of light is removed, it's called phosphorescence. So Becquerel's idea was that maybe it's the heavy elements that might emit these X-rays. And so he was looking at elements, and especially the minerals containing the element uranium.
So why did he predict or expect that heavier elements might do this? Was there some more reasoning behind that?
The idea was that these elements were more readily gave off more intense luminescence than lighter elements. He postulated that the heavy elements could take in the visible light, and then because they tended to give off a more intense luminescence, that they were also giving off these X-rays. Now, interestingly enough, at that point in time, people were using photographic plates as a way of detecting the X-rays. And the photographic plates were ones that were coated with a light-sensitive material. And so Becquerel then took these photographic plates, he took uranium minerals, wrapped them in black paper, and laid the mineral on top of the photographic plate. He would then wait until it was bright sunny, the sun was out. He would take them outside, take the black paper off of the mineral, and allow it to be exposed to the sunlight. And then after a period of time, take these plates back inside and develop them. And he found that indeed there would be an image of the mineral imposed upon the photographic plate. And this is all speculation, because I don't believe that Becquerel ever kept a notebook.
He never kept a notebook? So
at least I haven't run into somebody saying this is recorded in his notebook.
Wow. So the only way you could get enough energy to excite the uranium minerals was with sunlight, right? There was no artificial way of doing it back then. Yeah.
So the speculation is he prepared the same experiment again, wrapped the mineral in black paper, and then because it was not sunny that day, he left them in a drawer, not exposed to any light. And this went on for a period of about a week. And so at the end of that week, he thought, well, I'll go ahead and develop a plate. I won't find anything, but I'll develop a plate just to show that this was negative information, that it was the sunlight causing the luminescence, causing the mineral to expose the photographic plate. Instead, what happened when he did the plates is that he saw the same intense image of the mineral on the photographic plate. Now, what's interesting in all this is 30 years before, Abel Napris de Saint-Victor noticed a persistent photographic effect made on his plates by uranium salts. So 50 years before...
Someone else had already made the discovery.
Right, and published a paper in the French Academy of Science.
And it was published.
Yes, but nobody cared about it then. And Becquerel, they pointed out that this existed, kind of just blew over it.
So they brushed it aside a second time.
Right. And so then Becquerel began to study the characteristics of the exposure to sunlight and not sunlight. And he, first of all, showed that it was uranium mineral that caused the exposure. He then also showed that the image persisted. It went through black paper, it went through thin metals, and so it was very similar to that of what Röntgen had discovered in X-rays. Now, Becquerel also said that it was still a light that was doing this. It was light characteristics, and studied it as if it were light. Unfortunately, we now know that it wasn't light.
Yeah.
And again, there was another Englishman, Thomson, who published and found that uranium compounds produced invisible rays long after exposure to light and electricity. He reported this, but then dropped it because no one was really interested, and he never followed up on it.
So this discovery just kept getting brushed aside over and over again.
Yeah, Becquerel announced his discovery on March of 1896 and published about, I think, 7 or 10 papers that year. There were a couple of other papers by other scientists published about it, but within the next year, everybody had lost interest.
Why was there such a disinterest in this discovery?
Most likely because with X-rays, you could generate those with, if you had a Crookes tube and you had the power to form that, and the intensity of the X-rays could be controlled by the electrical power associated with the system. With what Röntgen called uranic rays, they were not very intense, and they weren't very useful. They didn't have that medical application that the X-rays did.
Yeah.
So Becquerel basically established his scientific priority, and then after a couple of years, the curiosity of these rays faded, and no one was interested. And it came to Marie Curie. She was at that point in time looking for a topic to study for her PhD, that she decided to choose this as a dissertation topic. So between 1896 and 1897, the interest in it completely faded away. And it was in 1898 that Marie Curie, looking for a topic, decided to investigate this as opposed to what everybody else had jumped on X-rays.
So he established the principles of this ray. So the person that discovered it and published it previously, he doesn't get credit?
No, it's more or less he who is the loudest and the longest seems to get the credit.
I guess so. So that's kind of interesting because I feel like nowadays that person would have gotten the credit before anybody else, even if you were loud.
Well, it was not an applicable discovery. It seemed like if you compare the discovery of X-rays to the discovery of and I will use the term radioactivity, but that was not developed by Becquerel. That was a term developed by the Curies. And so, it wasn't until the Curies began to investigate quantitatively the activity associated with the uranium materials that things began to develop. And that's going to be the source of our next topic.
Yeah. Yes, where I guess, the coining of radioactivity and where radiochemistry really is born from them.
And the discovery of polonium and then radium.
Mm-hmm. And adding to the very small periodic table.
Right. Uranium had been known since the mid-1700s. Mm-hmm. And it really had no use other than to color ceramics.
Yeah, that's one thing. If you're out there, if you ever wanted to see some phosphorescence of uranium, find old Vaseline glass, and you can put it under a black light, and you'll see how brightly they glow. Yeah,
and of course, if ceramic-wise, then you have Fiesta ware.
Yeah,
the orange color is due to the uranium.
When did they stop using uranium in Fiesta ware?
Probably in the 1950s.
1950s, so pre-1950 Fiesta ware. If it's bright orange, and it's pretty noticeable.
Oh, yeah.
And it carries quite a bit of activity as well compared to Vaseline glass. Mm-hmm. Just putting that up to a Geiger counter, you can immediately tell. How much uranium were they using in that coating of Fiesta ware? It seems kind of absurd.
Yeah, I've never seen any percentage. But,
and this is all natural uranium. And if you're ever wondering, uranium is not a scarce element.
Right.
Right. It's everywhere.
Yeah, it is. It is in seawater and in any phosphate deposits. And there are a number of natural sands that have a fairly high concentration of uranium and thorium.
It not being so scarce kind of lends it to being, I guess, discovered a little bit easier. But I was going to maybe talk about some other stuff with uranium, but I guess that'll be getting too far ahead. But
okay.
Is there anything else we would like to add?
Well, I think the next one or two times that we'll talk, we'll cover the actual determination, separation, and some of the things that Pierre and Marie Curie had to do in order to really begin to bring radium into the spotlight.
That's all we have for this podcast. We'll see you next time where we'll get into the Curies and really the birth of radiochemistry.